Let us continue with Chapter 4, Problems and Solutions, Part 3. The question: a straight horizontal conducting rod of length 0.45 meters and mass 60 gram is suspended by two vertical wires at its ends. A current of 5.0 amperes is set up in the rod through the wires. What magnetic field should be set up normal to the conductor in order that the tension in the wires is zero? What will be the total tension in the wires if the direction of current is reversed, keeping the magnetic field same as before? Ignore the mass of the wires, given G equal to 9.8 meter per second squared. So here we have a conducting rod which is placed in a horizontal position, and it is hung by two vertical wires at its ends, and a current passes through the wires, through the rod. So the value of current that is passing through the rod is 5 ampere. Now we have to first find out what magnetic field should be set up normal to the conductor in order that the tension in the wires is zero. So when the conducting rod hangs from the wires, the weight of the rod acts vertically downwards. Now this downward force is opposed by the tension in the wires. So tension in the wires will be in the upward direction, and that is because of the weight of the rod acting downwards. Now you know when current passes through a conducting rod, a magnetic force will be set up. Now we have to think of setting up a magnetic force in such a way that it opposes the gravitational force of the conducting rod. So let us see how to do the first part. So magnetic force which is set up in the conducting rod is BIL. Now this magnetic force must be equal and opposite to the tension in the wires. And what is the gravitational force acting on the rod? That is mg. So BIL must be equal and opposite to mg. From that we can calculate what magnetic field must be set up. So B is the magnetic field, and it will be equal to mg by IL. M is the mass of the rod given as 60 grams, and you have to convert it into kilogram. So 60 into 10 to the power of minus 3 kilogram. And G, acceleration due to gravity, is 9.8 meter per second squared. I is the current 5 amperes, and L is the length of the rod, which is already given in meters. So we can apply it directly as 0.45. So when you work this out, you get your answer to be 0.26 Tesla. So this is the magnetic field which will produce a magnetic force that opposes the gravitational force of the rod. And the direction should be upward direction. The magnetic field should be such that Fleming's left-hand rule gives an upward magnetic force. So the weight of the rod acts vertically downwards, and the magnetic force will be acting upwards. So tension in the wires will be zero. Okay, second part. B. If the direction of the current is reversed, what will happen? Then the magnetic field which we have set up will produce a magnetic force which will also act vertically downwards. So we have the weight of the rod acting downwards and the magnetic force also acting vertically downwards. So they add up. Total tension in the wires will be BIL plus mg, and when you work this out, you get your answer to be 1.176 Newton. Second question. The wires which connect the battery of an automobile to its starting motor carry a current of 300 amperes for a short time. What is the force per unit length between the wires if they are 70 centimeter long and 1.5 centimeter apart? Is the force attractive or repulsive. So here we have a connection, a circuit between the battery of an automobile and the starting motor. And these two devices are connected using two wires. So there will be a current flowing through the two wires, and the current will be flowing in opposite direction to complete the circuit in the two wires, and these wires are kept in a parallel position. There is a formula for force per unit length between the wires given by F equal to mu naught I square by 2 pi r. So mu naught is the permeability of free space, I is the current that passes through the wires, and r is the distance between the two wires. And as you can see, here we have the length of the wire and the distance between the wires are given in centimeters, so we have to convert them into meters when we calculate. So we get your force between the two wires as 1.2 Newton per meter. And because the two wires are in opposite, carry current in opposite directions, the force between the two wires will be repulsive.